Welcome to Rational Science. Today I start the class by dealing with inventions and inventors. And I start the class with a couple of questions. Who invented fire? Well, if you ask the Greeks, they would say it was Prometheus. And he came down from he came down from the Olympus, Mount Olympus, and gave fire to man. Okay, and it was Zeus who punished him by having an eagle eat his liver or his guts for an eternity. Okay, for doing that deed. Fire was supposed to belong only to the gods. But there's something wrong with that fable, that theory. And I guess the Greeks never figured it out because fire had been around already before man. Okay, they should have figured that out because you have natural fires, fires that get started by Mother Nature herself, or Zeus throwing his bolt and creating a forest fire or a jungle fire or whatever. And so when you trace it, you find out that fire's been around at least 470 million years ago, since 470 million years ago, since the Ordovician. Now, you don't have to believe that date because those dates are very flimsy, but for sure, for sure, fire has been around before man. Okay, because again, many fires start by nature, by lightning hitting maybe some dry leaves or whatever, and you have fire. So man discovered fire. Man did not invent fire. Okay, he ran into, like I keep saying, it's like when you discover the wall because you ran into the wall, and so what should they do? What should you claim that? Oh, I invented the wall, or I discovered the wall. Yeah, because you bumped into it, not because you broke your head trying to invent a wall, trying to devise a wall. And the same thing with fire. Fire, man bumped against, saw it. And the genius part, the inventive part was sticking a stick in there, pulling it out, and using it as a defense against other animals and maybe, hardening tools and cooking meat or whatever they used it for in the old days. Okay, how about the spear? Spear's been one of the longest standing weapons we've ever had, together maybe with fire and the hammer, right? And I'm not sure you could distinguish between a hammer and a knife, because one is sharp and the other one is dull, but they use these stones to hit things, okay? But then at some point they invented the spear, okay? And here's a couple of spears that they found, okay? They look more or less like this. These are maybe among the oldest spears out there. And some of these date to about 400,000 years ago. Some say there were spears already 500,000 years ago, okay? And in comparison, the knife, the one the stone knife, hitting something with a sharp edge, that was there for about 2.5 million years ago. So Homo habilis used that, so those are old artifacts. Okay, how about clothes? Here we wear clothes, right, today. And who invented clothes? Well, one of the funny ones is that they always paint Neanderthal with clothes, and he looks more or less like this. Went on the other side. Got a new mouse and I'm not used to it yet. Okay, so they always paint them, or they dress them up in clothes. And the question is, is it because Hollywood actors don't want to go nude on stage when they do Neanderthal parts? I think the Neanderthals were more like the guy on the right, which was the one drawn by Boulay, 1909? And I think Neanderthal did not use clothes. And the reason I think that is that his ancestors were around England. They found two-legged creatures in England 800,000 years ago. Supposedly, whoever those were and whoever was in France and in Germany at the time, two-legged creatures, they gave rise first to man of Heidelberg and then to Neanderthal, which came like maybe anywhere from 300 to 500,000 years ago. And so we're talking about 800,000 years ago. Were clothes around then? And so we had these two-legged creatures in England during the glacier times, right? Because you had these glaciers that were stretched all the way to England. So the England was like Arctic weather at the time. And so, yeah, if you have Arctic weather and you have no clothes, then that means man or some hominid got used to the cold in Northern Europe. And that's where Neanderthal came, and I'm sure he did not use clothes. There's no indication that there were needles used by Neanderthal. We haven't found anything like a needle. And we found no clothes, obviously. Now, people say, well, those things deteriorate over time, and so you shouldn't be able to find them. I don't think they ever used clothes at all. They had no need for it. They were like wolves today. You know, they sleep in the snow. And so why can't a monkey also sleep in the snow? Is the cold weather only reserved for mastodons and mammoths and wolves and bears? Can't be a monkey? And so, yeah, I don't think Neanderthal used clothes, and that must have been a distinguishing feature when humans came into Europe, assuming they met. They would have recognized each other as different species just by the clothes, let alone, you know, their appearance, other appearance. I don't think they ever met after, you know, even then. I think Neanderthals disappeared about 40,000 years ago, and humans, the first indication we have of the appearance of humans, in other words, where we have a skeleton, right, dates to 35,000 years ago, and that was in Romania. Okay, so Pestera Cu Ace is the cave, and they found a human there 35,000 years ago, and you know, Neanderthals, for what they see as far as the Mousterian technology, he disappeared 40,000 years ago, 5,000 years before humans entered Europe. So I don't think they ever met. And if any human really ventured into Europe, I'm sure the clansmen would have liquidated them. So that's maybe why we never see any humans in Europe until the Neanderthals are gone. Some people believe they made it. And that's the reigning theory today. Okay. How about the wheel? When did the wheel come into being? Well, for sure, Upper Paleolithic, you have no wheels. You don't have the wheel until the Neolithic. Less than 10,000 years ago, okay? And so here's who it's ascribed to or attributed to today. It's attributed to the Sumerians. And I'm sure it probably preceded the Sumerians themselves, but essentially they figured this out because of the potter's wheel, okay? They had to turn the pot around while they were molding it. And from there, they probably realized that the wheel could be used to put on a cart if they wanted to pull it with some horses or donkeys or whatever they domesticated at the time. And I think that's how the wheel came into being. Then they use it obviously for chariots in wars and so on. But the oldest wheel that we've found is Sumerians. And maybe you're talking about, I don't know, maybe 3,500 years before Christ or something along those lines. Okay? And certainly the Egyptians around the same time had the wheel, a little later, but you're talking about, again, maybe 3,000 to 4,500 years ago. Somewhere in between there, they had the wheel on carts. Okay, okay. So what is an invention? Let's find out by making a little trip. We're going to go on a trip, time travel. we're gonna play an Einstein here. We're gonna go and time travel, go through the time tunnel, and we're gonna go see some Neanderthals, okay? And we're gonna meet this fellow. His name is Org, and Org's gonna go to the patent office to patent his new invention. Okay, so here's Org. Okay, so Org goes to the patent office. Okay. And when the worker there says, hi, Org, what do you come here for? Says, I'm going to patent this thing. And what is that? Well, it's a club. Club, huh? What do you use it for? Well, I use it to bop other Neanderthals over the head of the neighboring clan. And I also sometimes use it on my wife. And it works wonders. Says, okay. I'll grant you patent number 3. Okay, looks like a good device that you could use there. Okay, there you go. Next day, another fellow comes in, and his name is Gore. So Gore goes in there, and patent clerk says, "Okay, what do you got, Gore?" "I have board." Board. What is board? Well, board is I use it to hit 2 Neanderthals over the head, to bop them over the head with. Works wonders. Okay, it sounds like a useful device. Okay, you get patent number 4. Okay, so we had 2 patents now, okay, aside from the earlier 2. Next day, another guy comes in. His name is Tron. Okay, say, hey, Tron, what do you got there? Well, I've got this device, which I made. I took Gore's idea, and I took also the other fellow, Org, and I built this thing. I put 4 of these clubs underneath this board, and this is the device. This is the device I have. So, what do you use that for? Well, I use it to bop people over the head with, but see, it's much better than handling just the board from your hands. You can grab it by any one of the legs and swing it around and bop people over the head with. Okay, I'll grant you patent number 5. Okay, okay. The next day we have another fellow. He's from the new generation. Okay, and unlike these guys, he's got a double syllable name. Okay, so he's known as Loon Boy. He comes in there and he says, I've invented this. What is that? Sounds like the same device that this other fella came in with yesterday. And said, well, I call it table. Table? What is table? Said, well, you can put your meals on the table and eat from the table. And you can also use a smaller one and you can sit on it, and we call it chair. Yeah, but we already have table and chair. We use them every day. They are made of stone. We are stone people. We are in the Stone Age. We don't use wooden things. Well, to make a long story short, he doesn't grant a patent to Loon Boy. Okay? And the main reason he doesn't, one of them is that it was not really an invention. It's the same thing that the other guy invented, but he just did something different with it. There was no new device. He just used it for something else. That was one of the issues. And the other one was this. It didn't work. When they put their mammoth steak on it, it broke the table. And they said, well, we can't use this, not for our mammoth steaks. And so, he didn't grant it because of that. But we have an issue here. And the issue is, did Loon Boy have an invention or an innovation? and there's a difference. Okay, and here we look at the definitions. We find in the both in the Wikipedia and the dictionary, and here you see them. Okay, what is an invention? Well, or what is it to invent? It says to originate or create as a product of one's own ingenuity, experimentation, or contrivance. Well, what are we talking about? Are we just talking about ideas? Because if you're just going to create, and then it says product, and what do we mean by product? Are we talking about a solid thing like a gadget, a thing, or are we talking about ideas? Just, for example, methods, processes. And so this is more or less like we just had Loon Boy. He came up with the same thing, but he's using it for something else. That's all he did. Is he going to patent that table and saying I invented table? Simply because he took the same device and just turned it over and said I have a different device. Okay, so we have to distinguish between, I guess, an invention and an innovation, a new use for that same invention, same gadget. Okay, Wikipedia has invention, a unique or novel device, method, composition, or process. It may be an improvement upon a machine or product or a new process for creating an object or a result. An invention that achieves a completely unique function. And this is what happens when people don't know how to define words scientifically, because there's so much gray in there. So much gray. It's got to be black and white if you're going to use it scientifically. But when you have so much gray, then people have different opinions, end up with different opinions on what an invention is and whether you have an innovation over an existing invention or just a cosmetic modification or whatever, So we have to distinguish. We've got to find out what an invention really is. Okay? And what is an innovation? It says something new or different introduced. Something new. A new idea, how to cook maybe. Different, cook maybe, soup differently. Bake a cake differently? Is that what innovation is? Or is it creating a new thing? Okay? And Wikipedia says innovation, the carrying out of new combinations. Okay? That include the introduction of new goods, new methods of production, the opening of new markets, the conquest of new sources of supply, and the carrying out of a new organization of any industry. Personally, I don't know what business has to do with innovation, especially in regards to the word as it is used in terms of patents or in terms of gadgets. Okay? Now, I worked in the industry, semiconductor industry, for many years as a process engineer, and one of our functions was to write specs. You have to change specs constantly. In fact, I would say that maybe on an average, I had to write a spec, modify a spec, about maybe once a week on the average. You have many specs for different machines. Sometimes you get a new machine in. Sometimes there's a new process. Sometimes you adjust the control limits. There's all kinds of things going on. And maybe on the average, I would say that I had to change the spec, one spec of my portfolio, once a week on the average. I think that was the same for all engineers. And if every time I change the spec, you're going to say, oh, you invented something new. That's not an innovation, that's an invention. Man, I should be given a bunch of patents for inventions, okay? And one thing you should be aware of, and I'm an expert in believe me, I had to copy these specs to distribute them. Why? Because the companies I work for, Intel and AMD, Advanced Micro Devices, the semiconductor chip companies, right? They do not patent their processes. their methods. And, you know, they're not the only company. I mean, you have companies like Coca-Cola. Coca-Cola, my father worked for Coca-Cola. And Coca-Cola never patented its process for making Coca-Cola. And they've had it since the 1800s, 1890, 1880s, I think it was. They invented Coca-Cola. Right? And the reason Coca-Cola doesn't patent it is a totally different reason than these chip companies. Chip companies don't patent because they don't want the competition, or especially other countries, from copying their processes. Coca-Cola is not interested so much in that. What they're interested in is something else. It's a selling point. They say, look, anybody out there who says they manufacture Coca-Cola, that they also produce Coca-Cola, they're wrong, because they don't know how we manufacture, how we produce Coca-Cola. They don't know the process. They don't know the method. Why? Because we've never patented it. And by not patenting it, you know, you don't have protection, but they don't want protection. Their protection is their word that they have a unique product because nobody can copy it because nobody knows how they make it. That's their slogan. That's their theory. That's their way of thinking. And so a lot of companies don't patent their processes. And semiconductor companies, again, I cannot imagine them patenting their processes because, like I said, I change the spec, one spec at least once a week on an average. And I wasn't the only engineer. There were other engineers also changing their processes like on a regular basis. And what are you going to do? Patent every time someone makes a change in the spec? So this is where the problem is. They can't keep it's an ongoing process to change specs and to change the process. And you're not going to patent every time you change the process because it changes almost every day from one region of the area, fabrication area to another. So the question is whether processes, methods, have anything to do with patents. Now, the patent office does accept patents for processes. Okay, they do accept that. The question is whether that makes any sense. And yeah, I mean, there's no other place to take your process. Maybe to the copyright office instead of patenting, you copyright. I don't know. The issue here is whether an invention has to do with a process or whether it just has to do with a new gadget, a new device. Okay, and I think that's where we should limit inventions and inventing. Okay, but that's my take on that. Okay, again, that's for the politicians to figure out what version of patenting they wish to pursue. Okay, I'm raising this because there were some people left behind in the Nobel world. Okay, and I'm gonna tie some loose ends today on those people. Okay, and the question again whether they invented something or whether they made innovations, cosmetic maybe changes to an existing product. Okay. Okay, and so the first issue here is whether I raised this issue a couple weeks ago, whether ideas are unlimited. And I'm sure a lot of people will argue, or most people will argue, that ideas are unlimited, and I think that's because they never thought about that in any way. But we can spend all day arguing on whether ideas are unlimited. The question is whether inventions, which is a subset of ideas, whether those are unlimited. And so the question is whether if you pull the last marble out of the bag, you know, there's any more marbles in there. Is the bag a bottomless pit where you can just draw inventions forever, or are inventions limited to a point where once you pull that last marble, there's no more marbles in there? That's going to be the issue here, okay? So keep that in mind. And I'm sure a lot of people would like to argue the contrary points. Okay, so I know I'm in the minority here. Okay, so here are the folks that got Nobels for inventing things. Okay, And I've covered some of these in the past, but I'll just run through them relatively quickly. You've got Albert Michelson for his optical precision instruments, specifically the interferometer. Okay, you have Gabriel Lippmann a year later. Again, these are the first 20 years of the Nobel Prize. They gave at least five Nobels for inventions, okay? And I want you to look at the type of inventions that these people got the Nobels for, okay? And Lippmann discovered a method, okay, for color photography. Okay? So he did some fancy stuff with color photography, and because he had this new method, he got a Nobel for that. Does that have anything to do with physics or science? Is that just technology? Keep that. That's the question we're going to get down to as well. Marconi, well known for working on telegraphy. He had a big fight with Tesla. They went to court. Marconi won. Then the United States government, 20 years later, 30, 25 or whatever, in the 30s I think it was, then they went against Marconi because he wanted money for stuff that he didn't do, or at least the government claimed that he didn't do, and so they had a big fight over patents. I covered this other fellow, Dalen, okay? He invented an automatic regulator for use in conjunction with gas accumulators for illuminating lighthouses and buoys. And the question is whether that deserves a Nobel. And again, I just want to mention that he was Swedish, same place where the Nobels come from, who grants them, okay? And in 1912, in fact, he went blind because he did a lot of experiments. One of them blew up in his face, just went blind, blinded him. And so, yeah, the question is whether there were more important inventions than this one. I mean, I mentioned, on the one hand, the Wright brothers, they invented the airplane. 1903, 9 years before, they had already a running airplane, which was certainly going to be used 2 years later, 1914, during World War I. And it developed quite swiftly. And no one ever received a Nobel for anything related to the airplanes. And so the question is whether an airplane is more important or had a greater impact on human life than what? Illuminating a lighthouse? So yeah, a lot of these prizes I think are political, and there I think you see proof, evidence, okay? 1920, last one in the first 20 years, succeeded in finding an alloy of nickel, okay, and steel, right? That registered almost no change in length and volume as a result of temperature changes. Okay, great. I mean, is that such an important thing for humanity to deserve a Nobel for that? But, and again, these are inventions, and the question is whether the Nobel should be given to science, specifically physics, because it's called the Nobel of Physics, right? Nobel Prize of Physics. And does this fall under physics, inventing gadgets? Okay. And again, were there more important inventions than the ones you just heard? Okay. I think the only one that really, to some degree, had a big impact from those, probably telegraph, right? But even that was changed over time, okay? Because I don't think anybody uses the telegraph per se today. They use, other stuff that's been more advanced. Okay. This is the second wave, and you can see the type of inventions changed. You'll see something changed here, and that's 20 years later, starting 20 years later after the last one was given for some kind of technology, some kind of gadget. First one was Lawrence, and he invented the cyclotron, which is an accelerator, okay? It's a cylindrical type of accelerator, and the particle goes like in a spiral. Okay, so he got it to go in a spiral with magnets, etc., and accelerated down the beam line. So because of that, they were able to use it to study what? Particles. So He got Nobel for his cyclotron. Next guy who gets one for technology, again, gadgets, okay, things, okay, for the invention of an apparatus to produce extremely high pressures. Great. So we have high pressures, okay. Next one, I covered him, Blackett, for improving, because the Wilson chamber was invented by Wilson. That's why it's called the Wilson chamber. Okay, and so he improved on it. And because he improved on the Wilson chamber in such a way that the mathematical physicists who work, the particle mathematicians, they can accelerate particles over there. Well, this helped them a lot, and they said, now we can see traces, and so on. The next guy, he improved the technique in order to study radiation and nuclear reactions, because he says charged particles moving through photographic emulsions leave tracks that can be examined in the images developed afterward. Okay, so now you can see the trace of a particle, if that's what they're seeing, a particle scraping through a gas, and this guy said, okay, we can take these fellow, he showed that you can take a picture of that. Okay, so that was his contribution. Again, we're talking about particles, we're talking about electrons, we're talking about atoms, ions. Okay, that's where they headed. You can see there's a little difference between the first 20 years to the inventions that started 40 years after the Nobel started being handed out. Glaser, invention of the bubble chamber, which replaced the Wilson chamber. Okay, put this gas in there and was able to look at the traces through the gas. And in '92, Charpak for his invention and development of particle detectors. Same thing as the others, but in particular the multi-wire proportional chamber. Okay, so they replaced a lot of this with wires, and eventually was replaced by semiconductors. Okay, so the chambers in which they study particles, or so they think they're studying particles, those have been modified over the years. That's what these guys got Nobels for. Okay. Next set of people, they're interspersed in between, okay, but they worked on microscopes and telescopes. They improved on different types of devices to be able to peer into the world of the small, okay. And so the first guy for his invention of the phase contrast microscope. Second guy, telescope designed to capture radio waves. And the third guy, for his fundamental work in electron optics and for the design of the first electron microscope. Okay? It's called SEM, Scanning Electron Microscope. I use those. I was certified on use of electron microscope. Then they came up with this other one about the same time, I guess, the Scanning Tunneling Microscope. Never used one of those, but same thing, is to peer into the world of the small. Can they take pictures or images or whatever of an atom? Yeah, like through a telescope. Okay, I mean, I use these things. I could see very deep. I never saw individual atoms or even arrays, because I worked at a level that didn't require that sort of detail. All I needed to do was identify what particle, for example, had fallen on my wafer, and you have this this graph that tells you what the chemical elements of that particle are. Okay, and for that you use a SEM to see it first, to locate it, then you find out what it's made out of, and then based on that you take decisions on what to do. Maybe you got to clean the chamber, maybe you got to clean the pumps that are maybe backstreaming into the chamber, etc. There's different procedures to fix problems in the fab, okay, fabrication area. And so microscopes help a lot for that. The question is whether that's science. I mean, what are we explaining with this, if that's what science is? If it's technology, well, does technology equal science? Okay, so this is the issue. I mean, you can invent a microscope, great, I mean, or telescope for that matter. Is that science? That's just a tool to help you work in the shop, in the manufacturing area, so to speak, maybe in the lab, okay, if you're a researcher. That's got nothing to do with explaining a phenomenon. Okay? And so these are two different branches, and the question is, do both belong to science? And you got to define science, the word science, in such a way as to encapsulate both of them. Okay? You got to incorporate the two notions somehow in your definition of science. And this is where the problem is, because if you do that, then you're going to include the word technology within science as well. Okay, because clearly invention of a microscope, a telescope, or a cyclotron, or a telegraph, all those belong to technology. Is technology a branch of science? Is it part of science? Is science a branch of technology? This is where we draw the line, and it's important to draw the line, make it black and white instead of gray, because otherwise people start talking in circles. You're talking about science and they're talking about technology, or vice versa. And, again, people have this problem because there are no solid definitions. They have not defined them crisply, rigorously, black and white sort of thing. It's all gray. This is the problem, okay? Okay, next group of people. Again, these are not chronological exactly. I mean, they're interspersed. I just pulled them out because they have a similar topic. Okay, that's why I pull these out. Okay, and so here's these fellows, and what do they develop, or what they invent? Well, John Bardeen, Shockley, and Brattain, they're known for developing the transistor. In the 1940s, I think, right after war, they developed it. By 1956, they got a Nobel, and I think the first one was a bipolar. There's two kinds, two general kinds, bipolar and MOS, metal oxide semiconductor, and I think they developed a bipolar. Okay. Kilby, for his part, in the invention of the integrated circuit. Okay, integrated circuit is many transistors, as well as other things in there. Okay, so it's a array of transistors with diodes and capacitors and resistors, etc., all made chemically. Okay, that's what a semiconductor is. That's what an integrated circuit is. And of course, because of that, they were able to get rid of some of these bigger things, which we still use today. We haven't gotten rid of them completely, but they had these printed circuit boards, which I worked on as well earlier in my life. You stuff these printed circuit boards with transistors, capacitors, etc., and they're used in different parts of the industry, of the electronics industry. Okay, Willard Boyle and Smith, what did they do? They invented an imaging semiconductor circuit, the CCD sensor. And again, that's the one that's used today to detect particles coming from space or whatever. Okay. And the last one was in 2014 for the invention of efficient blue light emitting diodes. And diodes, which has enabled bright and energy saving white light sources. So because we save on light, because they invented some new light emitting diodes, LEDs, right? You get a Nobel for that? Just inventing a little device? You would think that we're straying from the purposes of science. And again, is science technology? Is technology science? Is science about inventing gadgets? That's the question. Okay, the last group of people here that I'm going to cover today, and it's these folks, and they invented just a few things that are not specifically related to any of the other people. And the first one is, if electrons are elevated to higher energy levels with the help of heat and light, okay? So you shine light or heat, photoelectric effect sort of thing, okay? An avalanche-like effect occurs when they fall to lower levels. And these fellows contributed to putting this phenomenon into practical use in masers and lasers. So they worked on lasers. Okay, the next guy, he worked on the hologram. And the last guy there, he got his a couple years ago. And what did he invent? Optical tweezers. Okay, that's what he did. And what did they do? They grabbed particles, atoms, molecules, and living cells with their laser beam fingers. Okay, and the tweezers use laser light to push small particles towards the center of the beam and to hold them there. Okay, so they were able to manipulate with these tweezers. They were able to manipulate molecules and atoms, or so they claim. Okay, and yeah, it's possible, but the question is, those are tools. It's like saying I invented a hammer or a screwdriver. You get a Nobel for that? I mean, maybe in the days of the Neanderthals you would. That would have been, quite an invention in those days. And okay, so these guys are able to push, let's assume, atoms around. Okay, so you move them around. We still don't know what an atom is, what it looks like. Is it an atom an orbiting bead? An electron that goes around the nucleus? Is that what an atom looks like? They don't have a model for the most fundamental of atoms. And here they're giving Nobels for a guy who says, oh, I can push those atoms around. Well, maybe you can. What is it that you're pushing around? Can you draw it for me? And no, what he's pushing around is a little ball. And you say, if he's pushing a little ball, how can that possibly be if the atom, the quantum atom, is not a ball? It's an orbiting bead. And what he's pushing against, if quantum has its way, are orbitals. What's an orbital? Many orbits. That's why they called it an orbital. It's where you can find the electron bead somewhere within a certain volume. What's that volume made of? Energy levels? Is that what it is? Is that what the guy's pushing with his tweezers? Energy levels? Orbitals? Some abstraction? So again, we don't have an atom, but these guys are getting Nobels for it, saying, I pushed the atom around. And again, we have a lot of technology and no science. Okay? So we have to define what science is and what technology, distinguish it from technology or from inventing gadgets. Okay, and so here's science. We define it, rational explanations. Physics deals with causes and mechanisms. That's what you have to explain, and in order to do so, you need to do it with objects. Here in this side, we don't do much philosophy, except next week when my next time around when my son comes in, we're going to have another end of the month review and debate. Okay, so bring your questions. It's going to be real time, and then to contrast this, we have technology. Okay. And here you have a definition of technology: inventing, developing a gadget through trial and error. Okay, that's what it's about. And it's synthesized by Mr. Edison himself. I have not failed. I found 10,000 ways that don't work. And Tesla, who worked for Edison at one time, he had a good way of putting Mr. Edison in the right light. He said, if he, Edison, had a needle to find in a haystack, he would not stop to reason where it was most likely to be, but would proceed at once with the feverish diligence of a bee to examine straw after straw until he found the object of his search. Just a little theory and calculation would have saved him 90% of his labor. Okay? Yeah, in other words, Mr. Edison, apparently, if this is correct, and from his own words, you have to say that Tesla was correct, that that's how Edison worked. He was not an inventor. He was a guy who bumped into walls. And the way he had the time and money to do so, so he put his people to work on bumping into walls until he found the right wall. That's how he figured this out. So it's not like he was a genius in a sense that he thought and understood electricity and said, okay, I'm going to use this filament because I think it's a better material. No, he just tried one thing after another until he finally hit it. He says, oh, finally, I got the filament I need. And we don't use that filament today anyways, but that was the best they had at the time, and so he was able to sell it to thousands, maybe millions of people, and that's how he made his money. But that's different than saying, he sat down and he really figured it out. He didn't figure out anything. In fact, when he died, both him and Tesla, neither one knew what electricity is. And Tesla is famous for saying, towards the end of his life, that someday someone will discover what electricity is. Meaning he had no clue. Okay? Okay, so let's get on today with the questions and comments that people made last time. Okay, there were a few of them here. Go with the first one. He said, imagine you're sitting in a basement which is like a maze with lots of corridors. Unless it's not a complete bunker, you are still able to use your cell phone. Yeah, okay. Of course, photons behave like waves. Well, one thing is, if they behave like waves, are you saying they are waves? Okay, that's the first question. Otherwise, they wouldn't be able to reach you and your phone. Well, how do waves reach you and your phone? Do they go through walls? I mean, if waves go through walls, what are they made out of? What is a wave? And of course, when you look it up, like I showed a couple times before, they're a bunch of vectors. That's all a wave is. Magnitude and direction. And they have these vectors, mathematical vectors, moving. Very scary stuff. Waves move in all directions. Yeah, I know. All these vectors, Jesus. And around corners and try to occupy the whole space. But the individual photons, now he's talking about particles, right? Something condensed into some kind of ball, I guess, seem to be discrete particles. Yeah, somehow they are connected. Okay, how are they connected? What are they? Are they balls or are they elongated or stretched vectors that are waving or moving or whatever? So they are discrete particles, but still they aren't. Great, we learned a lot. It's confusing. Yeah, no kidding. I have given up on understanding this, but it's interesting. I'm glad that he starts out by saying, because this is the way people think, and he's saying, light is waves and light is photons. But I don't understand it, but they are, no doubt about it. And this see, how did he learn all this? He learned it by rote. He just accepted it through authority and accepted it and just believes it. He never stood back and said, well, how come I can't understand it? What is light? How can light be both a photon, a condensed, concentrated piece of ball or whatever, a little volume, and how can it also be extended? How can it be both? It never dawned on him that he's got a problem there, okay? Especially when he says, it is. He already believes, he's already bought into it. Why? On the basis of authority. And so here are the possibilities. Get this thing up here. Okay, here we have the photons. They're a bunch of balls just moving. Okay, we all understand that if they're balls. Okay, why they travel exactly straight and don't deviate, we don't know. Are they connected? We don't know. I guess not. Okay, then you have the waves, and they're like continuous, but what you're staring at is a bunch of vectors. That's all you're staring at. And how do you reconcile photons, little discrete particles, with waves? There is no way to reconcile them. And so you end up with some kind of thing like maybe the wave packet on the side. Okay, so it's already been invented, the wave packet, whatever that is. And maybe that's one way of visualizing it. You have the side view and the top view. Okay, here's the professional way that you can see this. And you can see here Mr. Penrose, who won a Nobel Prize the other day. Okay, this is his version. Okay, you take the photon, you add it to a wave, you end up with a twister. Okay, so we got the twister. Okay, that's the wave packet. That's professional. That's official. Okay, that's from a Nobel Prize winner. Okay, he broke his brains on that one. Okay, and so this is what we propose instead, that the photon and the wave, maybe they're talking about a rope. And yeah, you can imagine the ends of a rope. If you torque a rope that's tied to a wall or to something, you'll see that it causes a little bit of pressure, a thump on that surface. Okay, so we have the photon at both ends, and you have in between, you have what is known as a wave. In other words, the Maxwell wave, which is actually what? A rope. Okay, and you can see it's a three-dimensional entity, and it's twirling, that means you're going to get all these goosebumps moving along the rope. So the rope doesn't go anywhere, neither do any of the links. What happens is the links turn in place, they turn in situ. And by doing so, they create this sensation that something is moving from A to B. So yeah, there is a different version, and it's got nothing to do with particles, and it's got nothing to do with vectors moving through space, mathematical vectors. Okay, now next issue here, a fellow raises this issue, and he's, I guess, a flatlander. He says, I like your ideas. Oh man, when a flatlander likes my ideas, I tremble. Please don't say that, you make me look bad. Don't say that you love my ideas. Say that you hate me, okay? Please, please, you're making me look, you're embarrassing me, okay? But you need to prove scientifically that the Earth spins and moves through outer space. Prove scientifically? What the hell is that? How do you prove scientifically? Prove to whom, first of all? And scientifically, in science, we don't prove. In science, you know, we explain. We explain objectively so that you understand. That's all we care about in science. If you want to believe, you want someone to prove, to convince you, to persuade and recruit you, you got to go to Sunday school on Sunday and talk to your pastor, your priest, whoever, mullah. Okay? In science, we do not prove anything. The crazy belief is not that the Earth is as it presents to us empirically, planar, but that we are all flying around in a dark, endless void on a gigantic wet rock. Prove that. Again, he wants to be convinced. He wants to be persuaded. He wants to be converted. Okay? He wants to be able to embrace the globe theory, as I guess he's referring to here. And so he wants someone to convince him. And we don't do that in science. All we do is explain something so that you understand. That's all we do. Once you understood, make up your own mind. And don't ask for someone, don't look for authority. Don't ask for someone to convince you. You got to convince yourself. If you like what you see, you understand it, then go ahead, okay? Your rope theory is the same as all other gravity theories, unproven conjecture, hopefully. Yeah, it's not a rope theory. First of all, it's a hypothesis, and you need to understand the difference between a theory and a hypothesis, okay? But we don't prove either. We don't prove hypotheses or theories, okay? And so, yeah, hopefully it remains unproven forever, okay, because it's part of science. Once it's proven, it's part of religion, okay? And proven to whom? Well, to this guy. His neighbor still doesn't believe in it. So I don't know who you're going to prove it to, the Pope, the Dalai Lama, I mean, I don't know. What is the hypothesis in your case? The rope. The rope is known as a hypothesis, okay? And you got to know the difference between a hypothesis and a theory. Hypothesis is the object that you're going to present, the definitions, and the initial scene. You got to show the initial scene that serves as the basis for your theory. Your theory is the explanation of what happened. Okay, what you did with it. Okay? And liars and deceivers have sold us the wrong world. How do you sleep at nights, guy? Poor fellow. Anyways, here's the theory. Okay. Here's the proof that the Earth spins. Okay. And here's proof that the Earth moves around the sun. Okay, so we got it there. You can see how the Earth is going around the sun and how the Earth spins. Okay, I hope I presented the proof now. I hope you believe, okay, that that's the case. Okay, so you see the Earth spinning. You see the Earth also moving around the sun. Okay, that's for starters, just to answer your questions. Let's get this other one. Give me a second here. There it goes. They're way at the bottom, so I got to get them up here. Okay, here's why the Earth holds water and holds air. because that's one of the concerns that flat earthers have, that how is it that how is it that water curves around the earth, and no one has raised it, but it's in the back of their mind. Why doesn't air leave the earth? What keeps it tied to the earth, to the globe? Okay, I don't know how they explain it in the flat earth world, but in the globe it's very easy. If every atom is interconnected, as the rope model proposes, to all other atoms, then what you have is that an atom is pulled by or falls towards every other atom on Earth, no matter where it is around the Earth. And it doesn't matter if that atom is part of air or part of water. It's pulled inwards towards the center of the planet. Okay, and the reason for that, again, it's that the majority of atoms are in the opposite direction of where that atom is located around the Earth. Okay, and here's a issue of motion. Okay, how does he know that the Earth moves? Well, here you see a definition, and we start with that. Motion, two locations, two or more locations. Briefly, two locations. Does the moon move? Does the moon move across the sky? Does the sun move across the sky? If the moon moves, then the Earth moves with respect to the moon, because the Earth is occupying two different locations with respect to the moon. Okay? So what you have is the moon moving different locations. If the moon occupies two different locations with respect to the Earth, the feeling is mutual. The Earth moves with respect to the moon. You can't avoid that. If you want to move God, you can move him very easily. I don't care how powerful God is. I can move him with my pinky. All I have to do is move my pinky, and God's head, his chest, his legs, whatever he's got, is changing distance and location with respect to my pinky. And he cannot avoid it. I move God all day long. God cannot avoid being moved by me. Okay? And here's another version of that. You can see your car, and it moves around the Earth. It goes maybe from California to New York or whatever. If the car moves, the Earth moves with respect to the car. So the Earth cannot stand completely still and have the car move and not change location with respect to the car. So anything that moves in the universe, or like I say in my book, if you want to move, you have this frozen universe. Everything is static, nothing moves. All the atoms are there, but everything's just standing completely still. Okay? And let's assume God is a spirit. Okay? He's nothing. He's not corporeal. We're going to do a little black magic here. There's no other way of doing this. If God wants to move anything inside the universe, it's very, very simple. All he has to do is move one atom. He moves it from here to there. All the atoms in the universe suddenly change their location with respect to that atom. He has moved all atoms by moving one atom. Okay? So if anything moves in the universe, nothing is allowed to stand still and say, oh, the Earth doesn't move. No, if the sun is moving across the sky, if the moon is moving across the sky, if your car is moving along the road, if an airplane moves, if a boat moves, the Earth is moving with respect to those objects. The Earth cannot avoid it. It's changing locations with respect to the tires of your car. Here, you want me to move the Earth? Here it is. I'm moving the Earth with my finger. The Earth is changing locations with respect to the tip of my finger. Very easy to move things. Okay, all you got to do is just move. Okay, I think it's the same fellow, and he says the following. He says, I'm not interested in explanations. I'm seeking the truth. Absolutely loved it. Okay, so we have an argument, you and your wife, and she said, you cheated on me. And he says, were you there? Do you know? Or do you believe? Truth, well, one person believes in one truth, another person believes in another truth. One famous truth is the existence of God. And half the world population, I'd say more than half, believe that God exists. And God is there and does good things and blah, blah, blah. And other people say that God does not exist. And so the question is, who has the truth? How do we prove the truth? You go out there and ask God, what do we do here? Okay, does gravity exist? Well, how do you prove it? Well, you let go of a pencil. And you say, well, gravity pulled it down. Well, another guy said, well, I don't see anything between the pencil and the earth. So what is this gravity thingy? Does it exist? And some people say, no, it doesn't exist because I don't see anything. Another guy says, well, it does exist because the pen always falls to the floor. And so one guy is convinced and has the truth, and he says gravity does not exist. And the other guy says, no, I proved exactly the opposite. I proved that the truth is that gravity does exist. So no, truth has nothing to do with science. And here, just to rub it in, here you see the difference between science and religion. And where do we put proof and truth and fact and evidence? We put it on the right-hand side together with experiment, okay, and consciousness and all this nonsense that humans have invented, okay. Yeah, none of that has anything to do with science. Science is just objective explanation. You explain how you pulled the box up with a pulley, and people will look at it and everybody understands the same thing. You ask anybody, how did the box go up? And everybody will say, oh, you pulled it through the pulley, with a rope going through the pulley. That's objective. Everybody sees the same thing. Everybody can testify to the same thing that they saw. Everybody believes the truth. The truth is I pulled the box with a rope going around a pulley. How did the window break? I threw a stone through the window. That's how the window broke. Everybody saw the same movie. Everybody saw the same thing. Okay, very straightforward, simple. Okay. Now, you explained it to someone who wasn't there, who didn't see it. And you say, how did the window break? This guy says, I know. I saw the stone go through the window. I was there. And a detective comes in there and says, well, I don't know. I think it was maybe a dog that jumped through the window. And so who are you going to believe? And the guy will have all this reasoning saying, look, I can prove through reasoning that it was a dog that jumped through the window. Say, no, I was there. I saw the guy through a stone. And half the people will believe you and half the people will believe him. Who holds the truth? Mother Nature does. We can only believe, we can only first explain, in other words, create a theory. And then some people believe this theory and some people believe that theory. That's the way it works. We don't have the truth. Okay? And there is no such thing as proof. Proof is to you. When they prove it to you, for you, it's the truth. Not for your neighbor. So no, never bring truth, proof, evidence into science. That's for a jury. Jury is religion, remember. Who committed the crime? This guy. How did he do it? He went in there and killed this person. You believe that. And it's been proven to the jury, and they believe it, and they sentence the guy and send him, to the electric chair or life term or whatever. They believe that. And years later, they find out he's innocent, and they say, okay, we were wrong. They let him go after 30 years. Okay, one fellow says, look at this site, Bill. Okay, so I went to look at this site, and it's a site I've been before. I knew this fellow already. In fact, I had contact with him. Proponent of, his name is Wolfgang Smith. He's about 90 years old. And proponent of a new interpretation of quantum mechanics that draws heavily from medieval ontology and realism. I like that word, realism. He's a realist. He only deals with things that exist, okay? Reality, okay? What did he do? He separated the corporeal world, the real world, right, from the physical world, the one conceived by the physicists, meaning the mathematical physicists, meaning math, okay? The quantitative side of the corporeal world. He thinks that physicists are mathematical, or that mathematical physicists are physicists. They aren't. They ain't. Okay? And the issue is he's got two notions. He says, okay, on the one hand, we have the, it's there, it says the, where is it? One is the physical world, and the other one is the corporeal world. And the physical world is the math world of what he calls physicists, mathematical physicists, of which he is one, by the way. And the other one is the corporeal world, which he insinuates is the real world. Okay, so he says, this is math over here, but don't try to say that that's the real world. In that sense, he's right, okay? But what does he mean by the math world, the physical world, and the corporeal world? I thought physical and corporeal were synonyms, okay? At least they are in rational science. They're synonyms. So there is no difference between corporeal and physical. But he continues, he says, the most profound discovery of physics, okay, physics with quotations, non-local correlations which take place instantaneously without a transfer of energy. What is he referring to? He's referring to EPR, Einstein-Podolsky-Rosen entanglement, how you have two particles, okay, and you move this one over here, far away, millions of miles away, like in the case of the photon, and the photon shot out of the same atom here goes in the opposite direction. So one is spinning, you can say -1, or let's say -1, the other one's spinning 1, +1. And as soon as you change one of them, the other one changes instantaneously. So this fellow is saying there's no way to explain that, except, and he's Catholic, okay? He proposes vertical causation as opposed to horizontal causation. What the hell is he talking about? Okay, and let's find out. Okay, just in case you see him one of these days out there, you find him. Okay, so I don't waste your time, I'll just be brief with this fellow. Here's entanglement, okay, according to quantum mechanics. And the problem here is that, and I explain with clockwise and counterclockwise because that's how Mother Nature, that's all that Mother Nature understands. She doesn't understand -1 and +1. She understands clockwise and counterclockwise. What these people are saying is, if you look at it from one end and it's clockwise, the other end is counterclockwise. And as soon as you change one, the other one changes in the opposite direction, instantaneously across thousands of miles or millions of miles in distance. And you say, how can that possibly be? There's a problem here, because how did one particle communicate with the other particle instantaneously? And so what this guy proposes is what you see there on the upper right, God. That's the vertical causation. He's saying it comes from beyond. There's no way to explain this through quantum. And in that sense, he's right. You can't send a particle and do something instantaneously by throwing rocks, at another particle. But there is a way to do it, and here it is. You look at a rope from one end, it's clockwise, the other end had better be going counterclockwise to your pal who's at the other end. And when you turn the rope in the opposite direction, they reverse for both ends, okay? And that's all that's happening there. And I always like to present proof and evidence so that I can get to the truth and convince people and persuade them and convince them. From my end, it's going counterclockwise. Oh, let's get it here. Where is it? From my end, the rope is twirling counterclockwise. Hopefully from your end, it's going clockwise. And now I'm going to switch around. My end, the rope is going clockwise. And from your end, it had better be going counterclockwise. You can do this experiment at home, always in the presence of a trained relativist, okay, because it's a very dangerous, very expensive experiment, okay. So try it at home, put your friend on one end of a rope, you on the other end, twirl a rope in one direction, then the other direction, and see what each one of you experiences. Then you'll have proof and truth and evidence and all that good stuff that they have in religion. Then you'll believe. Okay, and another issue here. Oh, they're so far at the bottom to get them up there. Well, it says, can you show us this science dictionary? where an object is defined as that which has shape. That energy is a concept. Well, if you look it up, you don't have to take my word for it. Look in any dictionary, okay, whether scientific or ordinary, and you'll find object, anything that is visible or tangible. Okay, in fact, there is no definition in the World of Science dictionary. In this science dictionary, that was the definition. And where did they get that? It gives you a direct link to Wikipedia, which is allegedly an informal source. There is no scientific definition of the word object. All we have is informal definitions of the ordinary speech, and hopefully you don't accept things on the basis of authority. Hopefully you think them out and you find out the scientific definition of the word object. And the word object is absolutely necessary to do physics, because you can't do physics without an object. Very simple. What is energy? Again, a concept, the quantitative property. And they give an example. Chemical energy is the potential, blah, 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 blah. And property, quantitative property, potential, those are concepts. Okay? You go to the World of Science dictionary. The first one was the Science dictionary. This one is the World of Science. Energy, the name given to the ability, blah, 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 blah. Ability, potential, property, any of those are concepts. Okay? And just to rub it in, here we have the super duper scientific definition today in mathematical physics. Okay? And it comes from this fellow, and he says, it is important to realize that in physics today we have no knowledge of what energy is. When you look it up, it says energy is defined as the capacity. Okay, we see that everywhere. And another source says the quantitative property transferred to an object. How do you transfer a property? And anyways, if you transfer a quantitative property, you're transferring a concept. So there is no physical object called energy. Okay? And there you see energy on the upper right. You can see what it is. What is that? Is that just smoke? Okay, and then the other issue he raises, can you show us scientists that abide to a scientific method that doesn't include observation and experiment? Yeah, we have all kinds of scientists out there. You should look at one group. They're known as the Rational Scientific Method. And on Facebook, you can find them, and a lot of them use that definition. And they don't use experiment. And they don't. In other words, they use the definition of object, and they don't use experiment or what was the other thing he mentioned there? I think it was this one. Give me a second here. No, that's the wrong one. Get the other one. Oh, I think I lost it. Well, I can't remember the other word. Not important. Anyways, they don't use experiment for anything. You just have to explain. And anyways, science is not about democracy. Don't raise your hand. Okay. What we do in science is explain objectively. And for that, first you got to define the word science, find out what the word science is, and you can't look it up and just say, oh, this is what the majority of people believe science is. We don't care what the majority of people believe. Science is not democratic, first of all. Second, we don't raise our hands, we don't vote. This is not a jury trial. What we do is we reason and try to make sure that we can use the word consistently. Okay, and once you have that, then you have a scientific definition, an objective definition of the word science, and from there you move on. And as far as I know, science, as I showed a minute ago, does not include experiments at all. Okay, science is about explaining objectively. Once you understand the theory, the explanation, we're done with science. Okay, if you want to run an experiment to prove something to yourself, or to your friend, whatever, that's fine. Go ahead, persuade them. Go ahead. It's got nothing to do with science. The science part stopped at the objective explanation. Okay? That's the way we look at it. And if you have objections to that, it's very simple. All you got to do is put the word science, a definition, and defend it. Defending is important because anybody can come up with definitions and say, well, science is about God and the angels. You know, you can say whatever you want, but the question is, can you defend that definition? Okay? And use it consistently. You can still believe that science is God and angels for all we care. I mean, you'll believe whatever you want to believe. The question is whether you can step in a ring and defend your definition. And I think it's the same fellow. He says, we have filmed electrons using laser attosecond pulses. And there are some Swedes, so supposedly, allegedly, filmed an electron. That's what you're staring at there. Okay. And then he says, we have photographed the atom using atomic force microscopes. And if you look up images for atoms, for atomic force microscopes, you'll see these images. And when you look at them, you say, okay, I see a bunch of balls. You know, it's like you see these with a telescope. And so we have a couple problems. The first one is we can't see, and they have not been able to see, with atomic force microscope, with tunneling microscopes, with scanning electron microscopes, you cannot see an individual atom to the point where you can see the proton and an electron bead rolling around it. What you see are bubbles, balloons, balls. That's got nothing to do with the model that quantum says is their atom. Their atom, the one they do electricity with and etc., is this atom. This is a two-dimensional version of their atom, and that's enough to show that what they're proposing is that there's an electron bead, a little tiny bead, that orbits the atom and falls anywhere within those, what they call energy levels. And so the electron bead can be anywhere within that volume. And the only problem there is that first you don't see that if you look at those atoms at the bottom, okay, bottom left, you won't see that. Because if the electron bead is rolling around, at some point you should be able to see the proton in the center, which is 1,800 times more massive than the electron bead. If they can film the electron bead as shown on the upper left, then while it's rolling around, at some point you should be able to see the proton in between those orbits. But let's assume it goes so fast, the electron bead goes so fast that it doesn't allow you to see the proton center. We got a problem there first because the electron doesn't fly that fast to create a three-dimensional globular volume. That's the first issue. So you should be able to see between the time the electron bead is on one side of the atom and then on the other side of the atom, you should be able to see the proton. That's the first issue. And then the other issue is that when you look at the electron, it doesn't look like that little bead that's up there on the upper left. What you see are balloons. You see membranes there. So our atom, the one that's made out of threads, membranes, balloons, which is how professors and everybody else typically illustrates them in front of the class with balloons. You know, the orbitals, they put the s orbital, the p orbital, and so on. And when you see that, you say, well, maybe they are balloons and not a little bead that's going around for no reason whatsoever, and no justification for why that bead doesn't fall to the nucleus or why it doesn't fly away spontaneously. Why do you have to forcefully ionize an atom when, you know, what's keeping it in the orbit? What's keeping it within the volume, within those energy levels? That's what you got to explain. Why does the electron bead roll around a racetrack? Like if, you know, a horse can't go beyond the racetrack, some that fall over, but it has to run within the racetrack. Why is that so? And why does it jump from one racetrack to another, one in a smaller radius, one in a larger radius? Why does it jump back and forth? What forces it to stop there? Why does it continue rolling all the way to the center of the atom? Why doesn't it fly away? That's what you got to explain with a quantum model. And the pictures debunk, if anything, quantum mechanics. You don't see an orbiting bead. And certainly if there's an orbiting bead, you should be able to see the proton in the center at some point in time. What is this? Another of those, what do you call it, naked singularities that Mr. Penrose and Mr. Hawking supposedly proved. Okay, with that, we'll see you on Sunday, and I'm going to be with my son. We're going to have a duo, and we're going to take questions real time, so get your questions ready. Any questions on any subject. Primarily, we do physics and extinction. He likes philosophy, so you can bring your philosophy questions as well. We'll address them, okay? And so we'll see you on Sunday, same time, same station. We'll see you then. Bye-bye.